You ever look at a huge bridge and just wonder, how does that not fall down? It seems impossible, right? Well, the secret is something called statics. And today, we're going to get into one of the most important skills in all of statics, figuring out all those hidden forces that are holding everything together, keeping it all perfectly in balance.
I mean, that's the big question, right? How do engineers make sure a skyscraper or a bridge can handle its own weight plus everything we put on it? It's not some kind of magic trick, it's all about the math. There's this super precise set of rules they follow, and it guarantees that for every single force pushing down, there's another force pushing right back up. If you want to design anything that's supposed to last, you've got to understand these rules first.
So here's our game plan. We're going to start with the absolute basics, the rules of equilibrium. Then we'll get into drawing what's called a free body diagram, super important. After that, we'll actually solve for the forces, look at what happens when a load is spread out, and finally, we'll tackle a fun little problem called toppling.
All right, first things first, absolutely everything in statics, and I mean everything, starts right here. For any structure you can think of, a tiny shelf, a massive skyscraper, to stay standing, it has to be in what we call a state of equilibrium. So, what does that actually mean?
It's really just perfect balance. That's the best way to think about it. The object isn't sliding left or right, it's not moving up or down, and it's definitely not spinning around. Every single push, every pull, every little twist, they all cancel each other out perfectly. Because if they don't, the structure moves. And trust me, in engineering, unexpected movement is, it's a very, very bad thing. And this balance is governed by three simple, unbreakable rules. I mean, think about it. In 2D, an object can really only do three things. It can move side to side, it can move up and down, or it can rotate. So these three little equations make sure none of that happens. The first one says all the horizontal forces add up to 0. The second, all the vertical forces add up to 0. And the third says all the turning forces, we call those moments, also have to add up to 0. That's it. These three equations are literally all you need to solve pretty much any basic statics problem.
Okay, so we have the rules, but how do we actually use them on a real object? You can't just jump in and start scribbling equations. You need a map, a kind of blueprint of all the forces at play. And that's where the free body diagram comes in. I'm not kidding. This might be the single most important skill you'll learn in statics.
Basically, an FBD gets rid of all the junk you don't need. You just draw the object itself, like a simple beam. And then you draw arrows to show every single outside force that's acting on it. That means the loads pushing down, and this is the really important part, the invisible forces from the supports that are pushing back up. We call those reaction forces or just reactions.
And this is the translation process in action. On the left, you see the real thing. You've got a pin support, which is kind of like a hinge. It stops the beam from moving up, down, or sideways. Then on the other side, you've got a roller support. It stops the beam from falling, but it lets it slide horizontally. Now look at the right. This is how we draw it on the FBD. The pin becomes two reaction forces, a vertical one and a horizontal one. The roller, just one vertical force. See? We've just turned a physical thing into a clean, solvable map of forces.
Okay, so we've got our rules and we've got our diagram. Now it's time to put it all together. Let's use those equilibrium equations on our free body diagram and finally figure out the exact strength of those unknown reaction forces.
Let's work through a super classic example. So we've got this simple beam, it's held up by supports at points A and C, and right in the middle, there's a 10 kilonewton force pushing down. Now, your gut might tell you, hey, it's in the middle, so each support probably takes half the load, right? 5 kilonewtons each. And you'd be right. But in engineering, we can't just guess, we have to prove it. So our mission is to calculate the reaction at A, which we'll just call RAY for the vertical force at A.
The key here is being strategic. To find the force at A, we're going to do something clever. We'll take moments around point C. Now, why C? Well, because the reaction force at C is acting at point C. Its distance from the pivot is 0, and anything times 0 is 0, so its moment is 0. It just vanishes from our equation. That makes things so much easier. All we're left with is the turning force from RAY and the turning force from that 10 kilonewton load. We write out that simple equation, solve it, and boom, RAY equals 5 kilonewtons, just like we thought. All right, but in the real world, forces aren't always just a single arrow pointing at one spot. What about something like snow on a roof, or the weight of cars all across a bridge? Those loads are spread out. So let's take it up a notch and see how we handle these distributed loads.
This is what we call a uniformly distributed load, or UDL for short.
And you'll notice it's measured a bit differently. Instead of just newtons, it's in newtons times per meter. It's like a pressure that's spread out over a certain length. Now, that might sound way more complicated, but there's actually a really neat trick that makes it super simple.
And here it is, the big secret. We're just going to swap out that entire spread out load for one single equivalent point load, a single force that has the exact same effect on the beam. And once we do that, we can use the exact same equations we just learned. It's awesome.
So how does it work? It's easy. Just picture that distributed load as a rectangle. The size or magnitude of our new point load is just the area of that rectangle. So you take the UDL value, say newtons per meter, and multiply it by the length in meters. That's your force. And where do we put this new force? Right in the middle, at the geometric center of that rectangle. Once you've done that, the problem is exactly the same as the one we just solved. Simple as that.
Okay, let's look at a special kind of problem that teachers and professors love to put on exams. What happens when a structure isn't just stable, but it's right on the hairy edge of being unstable, when it's just about to tip over or topple?
Yeah, these toppling problems are all about testing if you understand equilibrium at its absolute limit. They'll show you a beam with a long overhang on one side and ask a question like, how much weight can you hang off the end before the whole thing tips over? And to solve it, you just need to know one crucial little fact.
And this right here is the golden ticket. At the exact moment the beam begins to tip, it's pivoting on one support, which means the other end is lifting up. It's completely off the other support. So what's the reaction force from a support that isn't even touching the beam anymore? It's got to be zero, right? And just like that, one of our unknown forces becomes a known value. It's zero. This changes everything.
This one insight gives us a super clear step-by-step method. First, figure out which support the beam is going to pivot on. Second, you set the reaction force at the other support, the one that's lifting off, to 0. Step 3, you take moments about your pivot point. And now, since one of your reaction forces has disappeared from the equation, you can easily solve for whatever it is you're looking for, usually the load that causes the tipping.
Okay, so let's wrap this up with the key takeaways. Remember, all of statics boils down to those 3 simple rules of equilibrium. Your most important tool is the free body diagram. It turns a real thing into a math problem. Any spread out load, a UDL, can be simplified into one single point load right at its center. And finally, for those tricky toppling problems, the secret is that the reaction force at the support that's lifting off is just 0.
So everything we've talked about here is the foundation. And now that you get the rules for a simple beam, think about this. How would you take these exact same principles and apply them to something way more complex, like a 3D structure, a giant crane, or the roof of a stadium? The geometry gets a lot crazier for sure, but the fundamental ideas of balancing all the forces and all the moments, they stay exactly the same. It's just a matter of scaling it all up.